All right, so we're going to start off today by talking about current voltage characteristics for NPN BJTs, and let that guide our discussion into the early effect. So the first characteristic curve we are going to look at is how our current IC behaves as a function of changing base emitter voltage under the constraint. Let's see. So if let's call this voltage here VCE. So that's the collector to emitter voltage is greater than VBE. So all that really means, if the collector to emitter voltage is greater than the base to emitter voltage, then VCB has to be positive, because that's just going to be the difference of those two quantities, which is a fancy way of saying this guy is in the forward active region, right? So if we plot IC versus VBE, what we should expect to see is something like this. For very small values of VBE, there's practically no collector current, and then as the VBE gets larger and larger and larger, we see some exponential growth. This curve should look practically identical to that of a diode, because it's effectively what's happening, right? The next curve that I want to look at, we are going to maintain a constant VBE So here is our transistor. For a constant value of VBE, I want to discuss how the collector current changes as a function of the collector emitter voltage. Right? Where this collector emitter voltage is nothing but VCB plus VBE. Okay, so this is going to look very similar to the plots that we developed on Monday, except they're just going to be shifted over to the right a little bit. Okay, so let me explain what I mean by that. So here's our collector current, IC. Here is the quantity VCE. And let's do the first one here in red. Okay. So this might look something like this. Where this guy is for a particular value VBE1 and therefore a particular base current. My thing will write IB1, and we might have a second curve. It's going to look something like this, where this guy is for VBE2 or a base current IB2, and we might have a third guy that looks something like this, where this guy corresponds to a base emitter voltage VBE3 and a base current IB3. And in each case, the base emitter voltage is getting larger and larger and larger. So effectively, if I were to draw a dashed line here, everything to the left of the dashed line is saturation region operation, and everything to the right of the dashed line is forward active region operation, where we're observing that our collector current does not depend on the collector emitter voltage, which is what our model IC is equal to IS times the exponential of VBE over VT tells us. When we were describing how a BJT transistor operates, I mentioned something about that equation. Well, let me write it down here. IC is equal to IS EXP VBE over VT. How that's independent, obviously, of the collector emitter voltage. So the assumption being made there is that the width of the base isn't changing, or is at a constant value. But we should be able to see pretty easily, based on our previous diagram, which I actually probably have up right here. So let me pull it up. Let's see, we were talking about forward active mode operation. Don't need to redraw this or anything like that. I just want to point something out. Here we go. As the base collector junction becomes more reversed biased, what do we expect to have happen to the width of the depletion region at the base collector junction? Should get larger, right? So as this junction becomes more reverse bias, which means the collector terminal is at a higher potential, because for a particular value of VBE, that means the base needs to be just at some finite voltage. So as the collector voltage becomes more positively charged, the electrons in this N-doped region should be attracted towards the collector, moving the boundary of the depletion region up. And as more charge gets uncovered, more positive bound charge gets uncovered by the this boundary moving up, more charge has to accumulate on the negative side, or negative charge needs to accumulate on the P plus side of this junction as well. So we should see that as for a reverse bias base collector junction, these boundaries start to stretch like so, which is going to decrease the effective width of the base. So let's scroll down literally just a little bit here. If we look at this equation for IS depends on the width of the base. So as the quantity WB gets smaller, what happens to IS and therefore what happens to IC? They both increase, right? So we should see some increase in the collector current for increasing VCB and in turn increasing VCE. This phenomenon is called the early effect, okay? So in the early effect, let me switch back to that other thing here. So when early effect is present, our second graph here should actually look more like this guy. Okay, and I'm just going to draw for one particular value of VBE. So if this is VCE, let's do the purple curve for the sake of argument. So it's going to look exactly the same in saturation. Why won't the early effect cause anything to change during saturation region operation? It's a great test question. So as I described the early effect to you guys a moment ago, as the base collector junction becomes more and more reverse biased, the width of the base is going to get smaller and smaller and smaller. In saturation operation, is the base collector junction reverse biased? No. Right. So that's why the early effect will have absolutely nothing to do with the operation during the saturation region, right? Since the base collector, the effect that we're going to see here is fully dependent on the base collector junction being reverse biased, so it can't affect saturation region operation where the base collector junction is forward biased. All right, so with early effects ignored, we should expect to see a constant value for our current IC. With early effects included, as the quantity VCE gets larger and larger and larger, the reverse bias voltage across the base collector junction gets larger and larger and larger, which means the width of the base is getting smaller and smaller and smaller. And so we should see that IS and therefore IC have a linear increase. So something like this, just simply a straight line, but tilted up. Okay. Where mathematically, this current IC looks like IS EXP VBE over VT multiplied by a factor of 1 plus VCE, the collector emitter voltage, divided by VA, where VA is what's known as the early voltage. VA is nothing more than the x-intercept of that sloped line. So what I mean by that is if we continued it on to the left at the same slope, wherever that line crosses is the negative of the early voltage. Okay. Typical values for early voltage range from 5 volts to negative 150 volts. Okay. So in your homeworks, exams, and all that kind of stuff, if I say VA is equal to infinity, what that means is that the early effect can be ignored. Because for VA is, so the smaller VA is, what does that mean about the slope of this guy? Larger and larger and larger, right? So if VA is infinitely large, that means the slope is 0. or this guy just settles to IS times the exponential of VBE or VT, meaning this guy right here can just be thrown away, okay? How do you think the early effect is going to show up in our large signal model? Well, our equation for IC changed. That's it. Literally it. We just used the new equation for IC. Okay. All right. So any questions regarding the early effect? We're going to revisit this when we start talking about amplifier circuits, because it will have a very prominent effect that small signals will see much more so than what we're going to see with our large signal analysis. Okay, everybody reasonably okay here? All right, so let's move along to NPN BJT. DC biasing network. So these are common ways that BJTs are used in analog circuitry to provide a stable operating point for an amplifier. Okay. So the first that we're going to look at, we did an example problem on it Monday, is what I'm going to call simple biasing. All right. So for a simple biasing BJT network, we have some power supply voltage VCC. We are going to have some collector resistance R sub C. Here we have our NPN BJT. Our emitter terminal will be grounded. On the left-hand side, we are going to have some base resistance RB, like so. And so our operating point is going to be defined by our base emitter voltage VBE and our collector current IC. And another important thing will be the quantity VCE. Because VCE as compared to VBE will tell us whether or not our device is actually operating in the forward active region or the saturation region, okay? So our goal here is literally just to develop an equation or system of equations if necessary that will tell us what our DC operating point for the circuit is, meaning we're just trying to determine quantity VBE, IC, and VCE, so we can tell in what region this thing is operating and then what those voltages and currents are. Okay. So let's start by applying Kirchhoff's current law, Kirchhoff's voltage law on the left-hand side. Okay. So using KVL, we can see that VCC will be equal to our base current IB. So I'm going to go ahead and label that guy real quick. this is our base current IB, multiplied by RB plus the quantity VBE. Everybody okay with that? Anything wild or crazy? Our base current IB must then be VCC minus VBE divided by RB and our collector current IC is then simply beta VCC minus VBE over RB. If we apply Kirchhoff's voltage law on the right-hand side of this circuit, here, what we'll find, let me put left-hand path, for the right-hand path, we'll find that VCE is equal to VCC minus IC times RC, and therefore VCE is simply VCC minus beta VCC minus VBE divided by RB multiplied by RC. And if for whatever reason we wanted to know what our emitter current was, we just sum these two guys together. Right? So these equations should tell us everything that we need to know about the behavior of an NPN BJT in a simple biasing network. One other brief relationship that I want to introduce here is in order to maintain operation in the forward active region. So it should be obvious. Forward active mode requires VCE to be greater than VBE. So that can tell us what the maximum value of either RC or RB could be to keep this guy in that specific biasing condition if we know the other one. Okay. So let's put this set of equations into use. Let's say that I have the following circuit where I have a power supply voltage of 2.5 volts. I have a 1 kilo ohm resistor for RC. a 100 kilo ohm resistor for RB. Let's define our base current here, IB. Our collector current here, IC. Our base emitter voltage, VBE here. And our collector emitter voltage, VCE here. We are given that beta is equal to 100. And IS is equal to 10 to the negative 17 amperes. So what we're going to have to utilize for this particular circuit is an iterative procedure, much like what we developed for dealing with diodes. Okay, so we're going to have to take a reasonably educated guess as to what our base emitter voltage is, calculate the collector current, and then see if that collector current corresponds to that base emitter voltage. Okay. So for iteration number 1, let's guess that VBE is 0.8 volts, which for silicon-based BJT is a reasonable starting point. Somewhere between 0.7 and 0.8 volts is usually where we would start. Okay. So from this, our collector current, IC, would be 100, which is beta, times 2.5 volts minus our guess value of 0.8 volts for VBE, divided by our 100 kilo ohm resistance. And we would find that our collector current comes out to be 1.7 milliamps. For iteration number 2, we can say that our base emitter voltage, VBE, is simply VT times the natural log of IC over IS. This guy comes about from simply rearranging our equation for IC as a function of VBE. So if we plug in our numbers here, we'd find that we have 26 millivolts times the natural log of 1.7 milliamps divided by 10 to the negative 17 amps would give us 851.937 millivolts. And if we plug that value into our equation for IC, we start up here. IC is equal to 100 times 2.5 minus 0.852 divided by 100 kilo ohm. We would find that our collector current is 1.648 milliamps. Okay. So our initial guess generated a current of 1.7 milliamps. We use that to calculate a voltage using our IV relationship for our BJT. We recalculate IC, and if there was a change, and we need to keep going until that change is small, right? So right now our change is about 50 microamps, 52 microamps, I think exactly, right? Well, 52 microamps is a reasonably large percentage of our initial value of 1.7. So we need to at least do one more iteration to kind of see where it falls. Okay. So for our third iteration, we would have VBE is equal to 26 millivolts times the natural log of 1.648 milliamps divided by 10 to the negative 17 amperes, giving us a value of 851.130 millivolts. So we're changing by, let's see, somewhere in the ballpark of 800 microvolts here. And when we calculate, sorry, it scrolled, IC, we're going to have 100 times 2.5 volts minus 0.851 volts divided by 100 kiloohms, which will again be equal to 1.648 milliamps with rounding. So effectively, this third iteration tells us where we've settled because we don't see any significant change in the operating point, right? So the change in the voltage is very small. With regard to our initial guess, the change in the current is also very small in regards to our initial guess, so we can stop, all right? Now, I walked you through the iterative procedure because for whatever reason, sometimes your calculator will just crap out and tell you there's no solution, but it should be fairly straightforward here. That we could develop a single solvable equation using this guy and this guy, effectively. Substituting in this relationship for VBE into this guy gives us a single variable IC that we could use to calculate IC directly using a numerical solver on our calculator or whatever. And then from that, we could back calculate out what VBE is and know all the other quantities. So this is the, oh shit, my calculator doesn't work, or I have a peasant calculator or whatever reason method. And then obviously we can develop simply by substituting this guy into this guy, something that your calculator should be able to do. I'll call it 95% of the time. MathCAD should be able to do all that kind of good stuff as well. All right. So we have settled down to a specific operating point that I feel pretty good about. All right. How do we test whether or not this guy is actually operating in the forward active region? Because all of our analysis has made the assumption that we are operating in the forward active region. Right. So that's another key part of this. Okay. So this keeps scrolling slightly too much and it's ticking me off. VCE is going to be 2.5 volts minus our 1 kilo ohm resistance times our value of IC. Somebody throw those numbers in their calculator real quick and tell me what you get. I get about 852 millivolts. So is this guy operating in the forward active region? Yeah, it's at the very edge of saturation for sure, but it is operating in the forward active region. So what could we do to push this guy further into the forward active region, right? What if we weren't comfortable with biasing this guy on the very edge of saturation? Now, for a BJT amplifier, being at the edge of saturation really isn't going to mess things up too much, because we know that soft saturation, behavior in the soft saturation regime is effectively almost the same as behavior in the forward active regime anyway. So as long as we didn't have an amplifier that was going to push this guy too far one way or the other, we'd be pretty stable here, right? But as we get into MOSFETs, where this dissimilarity between what's called the saturation region in a MOSFET, which corresponds to the forward active region in a BJT, and the triode region in a MOSFET, which is effectively the same as the saturation region in the BJT. Yes, I know that's confusing. No, I don't have a solution for it. But we'll find that we don't have that same nearly similar operation, right? So we should probably not get in the practice of biasing things right on the transition point between two operational modes, okay? So our choices here, if we're stuck with a particular NPN transistor having a particular value of beta and a particular value of IS, our choices here are either change our power supply voltage, change our RC value, or change our RB value. So let's leave VC alone for right now. If we decreased RC, this value would obviously get larger. If we increased RB, that's going to cause a decrease in IC, making this value get larger as well. So if we want to push things for this biasing scheme more into the forward active region, we need RC to either be smaller or RB to be larger. That seems reasonable. All right, so a couple of things about this biasing scheme. Since the quantity VCC minus VBE determines the base current IB, this biasing scheme is very sensitive to power supply fluctuations, which means if we have a small change in the power supply voltage, we're going to see a large change in the operating point of our system. So the next couple of schemes that we're going to work with are going to try to overcome some of these limitations here, right? Another problem is that the collector current is obviously very dependent on beta, right? Right here. Beta, again, is simply the ratio of the collector current divided by the base current, both of which are temperature dependent, which means beta is highly temperature dependent, which means this particular biasing scheme is very finicky with regards to temperature, right? So as a homework problem, I'm going to have you guys analyze the circuit and then tell me what results with a small change in a small increase in power supply voltage, a small decrease in power supply voltage, a small increase in beta, small decrease in beta, to kind of show me how big those variations are due to those dependencies. Okay. All right, so our next biasing scheme is what's called a resistive divider biasing network. So in a resistive divider biasing network, we might have something like this. We have our power supply voltage, VCC. We have our collector resistor, RC. Here we have our NPN BJT. And then on this side, instead of having a single resistor, we are going to have two resistors. R1 and R2, like so. Here's our quantity, VBE. Here's our quantity, IC. Here's our quantity, BCE. Okay. So this guy is a little bit more difficult to analyze because we don't have a simple and straightforward relationship dealing with our base current, right? So we are going to employ Thevenin and Norton equivalent circuits to simplify this guy to something we can handle much more easily, okay? Now, we have to be very careful when applying Thevenin's theorem here because you guys may or may not remember this, but Thevenin's theorem tells us that we can replace any two-port linear electrical network with an equivalent voltage source in series with an equivalent V Thevenin in series with an equivalent resistance R Thevenin, right? This guy ain't linear. Okay. Our BJT, by definition, large signal operation, is not linear. But these two little resistors over here are. Okay. So I don't have to include the whole thing in my Thevenin equivalent. I can just look at a part that is linear and get the equivalent of that and see what falls out. So by that, I mean, if we take just this portion, VCC, here's R1, here's our terminal, here's R2, we'll put ground down here. Here's our terminal. This is a two-port net, or excuse me, a two-terminal network, right? There's one terminal, here's another terminal. I've disconnected this completely from the nonlinear portion of our network, so I should be good to figure out what V Thevenin and R Thevenin are. So V Thevenin in this case is just the voltage drop over resistor R2. What should that be? Voltage division. So do it. VCC times R2 over R1 plus R2. Oops, I screwed that up. Well, actually, VCC R2 over R1 plus R2. I'm gonna save it. All right. Now we need to find the Thevenin equivalent resistance. To find the Thevenin equivalent resistance, we have to deal with a dead network, which means we turn VCC off, so it's going to be ground. Sorry, what was that? I disagree. Yeah, if we turn that off, so we turn off a voltage source by shorting it out. So if the negative polarity terminal of the power supply voltage was at ground, then we just have a short to ground, right? So we're going to have R1 up here. R2 here. we're looking in. So what do we see? R1 in parallel with R2. Or let's not call it REQ, let's call it RTH. So just so that we're consistent. So that means this circuit up here is electrically equivalent to this guy. Which looks very similar to our simple biasing network. Right, where VTH, this just means I have a voltage source VTH with respect to ground, just like I was applying that's just shorthand notation, just so you're clear what's going on. Okay. So it should be trivial now to see that I now have a well-defined base current, IB, IC, VBE, and VCE. So the only difference in our analysis here is that instead of using VCC in the determination of our base current, we now use VTH. Okay. So we can see, we'll carve this out right here. VBE will be VTH minus IB times RTH. It must also be equal to VT times the natural log of IC over IS. From this, IB is VTH minus, what the hell happened? VT natural log IC over IS, all multiplied by a factor of 1 over RTH. Running out of room here, so I'm going to delete that line, which is nothing more than VTH minus VT natural log beta IB over IS, all multiplied by 1 over RTH. So I've given you an equation here that says the variable I don't know is some function of the variable I don't know that I can throw into a numerical solver if I need to. And then finally, down here, you can say that IC is equal to IS times the exponential of VTH minus IB RTH divided by VT. So once we know IB, we can solve for IC, although we could have just multiplied by IB by beta to get the same damn thing. But we've got a couple of different relationships that we can use here. All right, so what about VCE? What's going on there? Literally the exact same equation we had for the simple biasing network, right? VCE will be equal to VCC minus ICRC, or VCC minus beta IBRC. So we should have enough information here to figure out literally any of those quantities that we want. Because we only have a little over 20 minutes left, I'm not going to bother with a example problem here. One thing that I do want to point out a quick and dirty method of effectively applying this biasing scheme, or at least analysis when applying this scheme, is to neglect the effects of the base current entirely. So effectively just saying that if beta is really large and the base current is really small, VBE is just VCC times R2 over R1 plus R2, just using voltage division to get a good approximation of VBE and then going from there. That's really only valid though when, I think I had it written down here. Let me double check. The constraints for it being negligible. Let's call it. All right, let's write it down here. So we need IB, so for neglecting base current, we need the determined value of IB, or let me write this, IC over beta, to be much, much smaller than VCC over R1 plus R2. So what that means fundamentally is we're making the assumption that practically none of the current branches off and flows into the base terminal. It all flows down to ground. So if VCC over R1 plus R2 comes out to be, say, 20 times larger than what you get by simply taking IC over beta, that approximation is fairly valid. But I truly believe that not worrying about that approximation isn't that hard to get the actual values anyway. But as a practicing designer of BJT circuits, sometimes you don't want to go through all that damn math. All right. So our last, well, it's not our last, but it's the last one we're going to get to cover today. Network is what I'm going to call the full biasing network. Okay. And it is very similar to what we just saw, but with one critical difference. And this difference here fixes a problem with the resistive divider biasing, okay? So let's call this guy RC. We're gonna do what's called emitter degeneration. That literally just means putting an emitter, or excuse me, putting a resistor between the emitter terminal and ground. And let's call this guy R1. This guy R2. All right. So let me define my quantities here. Here's VBE. Here's IC. Here's VCE. All right. So the problem that this is fixing is that there's still some dependence on power supply voltage in establishing our biasing point in the previous scheme, okay? Now it's smaller because of that resistor biasing network, right? So if VCC changes by 5%, Vthevenin is going to change by a value that's less than 5% because of that network, right? But there's still going to be some small perturbation, which can lead to a reasonable change in the collector current. What this emitter resistance does is effectively lets the quantity VCE and VBE float a little bit. So this resistor serves to absorb some of the perturbation and minimize its effects, okay? So to analyze this guy, we're going to actually have to use our large signal model, but it should be fairly obvious that we can use the results of our previous analysis to simplify this guy by putting Vthevenin in series with Rthevenin on the input side of this guy, on the base side of this guy. So our large signal model should look something like this. Here's Vthevenin. Here's Rthevenin. So this is taking the place of VCC, R1 and R2 for the left-hand side of the circuit. Here's our base terminal. Between the base and the emitter, we have a forward bias diode over which a voltage drop of VBE occurs. We have our base current IB here flowing into the emitter. On this side, we have our collector carrying a current of beta IB. Connected to the collector, we have our resistor RC. And then between that leg of the resistor RC and ground, we have our power supply voltage VCC. And finally, between the emitter and ground, we have some resistance R sub E. Like so. So this guy is IC. This guy is obviously IE. So let's start with something simple. Does this large signal model make sense? Anything seem wonky or weird? This is legitimately the first time we've reached a circuit where we kind of have to use it to figure out what the hell's going on. All right. So anybody got any questions, comments, concerns here? Nobody's saying anything, so I'm going to move forward. All right. So if we apply Kirchhoff's voltage law on the left-hand loop of this circuit, left-hand loop, we should see that our Thevenin voltage VTH is RTH times IB, so that's the voltage drop over our resistor RTH. Then we have the voltage drop over our base emitter diode. And then we have the voltage drop over our emitter resistor, RE, like so. And we can do a couple of substitutions here. Right. So we'll have RTH times IB plus VBE plus RE times 1 plus beta IB. So I've done nothing here but express my emitter current in terms of my base current. We know that IC is beta plus, or excuse me, beta times IB. We know that IE is IB plus IC. So we have IB plus beta IB gives us 1 plus beta IB for our emitter current. Nothing wild or crazy there. And we can rearrange this a little bit again. Really, there are two ways that we could do this, but I'm going to do it in this particular way. So we have VBE plus a factor of RTH plus 1 plus beta RE multiplied by IB, where IB is 1 over beta IS times the EXP of VBE BT. So we have one equation, one unknown in terms of VBE, so that we could solve for VBE, and then from that, obviously, IC, IB, and IE. We know that IC is equal to IS times EXP VBE over VT. IB is 1 over beta IC. IE simply IB plus IC. And our last quantity that we need to figure out is VCE. And we can figure out VCE, which is the potential difference between here and here, just by applying Kirchhoff's voltage law around the right-hand loop, right? So we're going to have VCE will be equal to VCC minus the voltage drop over RC, which is just RC times IC minus the voltage drop over RE, which is just RE IE. And if we wanted to simplify that a little bit further, but it's really not necessary once we know all of those other parameters, right? So for this guy and all the other circuits, again, the quantity VCE needs to be larger than the quantity VBE to keep this guy in the forward active region. All right. We'll talk about one more biasing circuit very briefly. Actually, we got 10 minutes. We can do it now. Anybody have any questions about the analysis that we did to figure out where this guy operates at? All right. Our last biasing circuit is an interesting one. It's what's called the self-biasing network. So in a self-biasing network, we have our power supply voltage VCC, our resistance RC. Here's our transistor. I'm going to ground this leg. And we're going to put a resistor here. RB like so. Okay. So this voltage will be VBE. This current is IB. This current is IC. This current is obviously then IB plus IC is equal to the emitter current. All right. Is it feasibly possible for this circuit to operate in the saturation mode? All right, so this guy right here is VCE. Shouldn't matter. So let me explain what I mean by this, okay? VCE, using Kirchhoff's voltage law here, will always be the voltage drop over resistor RB plus VBE, which means it's always higher than VBE. So this circuit literally only works in the forward active region, forward active mode. Cannot hit saturation. Okay? It's not used for, it's used for some amplifier circuits, but the full biasing network is used much more often. And it's because we can't apply an additional signal to the base without messing things up. Right. So this guy is used sometimes for what's called common base amplifiers, which means absolutely nothing to you all now, but hopefully in about 2 weeks' time we'll mean something very, very specific. But it is a type of biasing network that can be used for amplifiers, so we need to cover it real quick. Okay. So our circuit analysis here is going to be pretty straightforward. We can see VBE is equal to VCE minus RB IB. We can see that VCE is equal to VCC minus RC times IB plus IC, which is the same as VCC minus RC times 1 plus 1 over beta IC. Everybody okay with where these guys came from? Just Kirchhoff's voltage law along the right-hand side here. And so from these relationships, we can get VCC minus RC over 1 plus 1 over beta IC is equal to VBE plus RB over beta IC. And we can get VCC minus VBE is equal to RC multiplied by 1 plus 1 over beta plus RB over beta IS EXB VBE over V2, giving us one equation, one unknown relationship for which we can solve for the operating point of the circuit. And once we know VBE, obviously IC is just IS EXB VBE over VT. And then IB is 1 over beta times IC, and IE is beta plus 1 IB. All right. Okay, that's enough out of me, and we're wrapping up 4 minutes early. I hope you guys enjoy your long weekend and all that kind of good stuff. I hope to have your exams grades to you by the end of the long weekend class on Wednesday at the latest. I cannot return your exams to you because there was a couple of people out with COVID. So we have to wait for them to take it before you can actually like see your results, but I'll at least have your grades to you. All right. And then depending on how awful they are, which is what you guys seem to think is going to happen, we'll talk about what we can do to mitigate that.